Okay, in this video I want to pick up where we left off from last week. We just completed a test on limits, continuity, and the difference quotient, and now we'd like to talk a little bit about where we're going with all of that stuff. So what's the big deal with using especially the difference quotient and limits? And the main focus for this class is using those definitions essentially to compute what we call the derivative of a function. So we're going to get into that a little bit here in just a moment, but let's just remind ourselves of what we've done so far. Last week we were talking about slopes of curved lines, and we can find the slope of a secant line by simply taking some y value. So we would generally call this one y2 and this one y1. If A is our point of focus, some position on the x-axis, and then h is some horizontal distance to the right of that, or left, I suppose. H is some horizontal distance away from A. Well, by substituting A and A plus H into the function, we get two Y values. And we would have had two X values, but if you think about this, our first X value is A plus H, and we subtract our second X value, which is just A, and that's where this H component comes from. Now, we recognize that the best approximation, if you will, for the slope at a single point is to reduce this h value to 0. If we had some large h distance, then the straight line or the secant line that's formed between these 2 points that are generated, well, that's an approximation for the slope at a particular point, in this case P. It's not a very good one because the horizontal distance is too far, and in order to better our approximation, we take this horizontal distance and we reduce it as much as we can. So we've got a large horizontal distance, and as we reduce this horizontal distance, well, we start generating a line that has a better approximation for the slope at point P. And the issue that we run into, of course, is that we can't allow h to be 0. If there was no horizontal distance between 2 points, well, then this particular definition fails, and we don't have the slope at a single point. We'd have to divide by 0 to do that. And so we account for that by introducing limit notation, and the limit notation along with our difference quotient will then ultimately give us the slope of a tangent line. And we did talk about in class some of the benefits for calculating the slope of a tangent line in terms of rates of change. Okay, we use that phrase, and anytime that you see a rate like miles per hour, cost per gallon, acres per day or something like that when you're harvesting, all of these rates can be established by simply looking at a graph that's created appropriately and labeled appropriately. So computing the rate of change is important, and what is often most important is computing our instantaneous rate of change as opposed to an average rate of change. So if we didn't make that real clear here, average rate of change is the slope of a secant line, whereas an instantaneous rate of change, the rate of change at one particular instant, is the slope of a tangent line. And hopefully all of that still remains clear to you. We spent a fair amount of time chatting about that last week. What I'd like to do today is just really emphasize the ways that we can find equations for instantaneous rates of change, and we can do so a little bit more quickly. Now, if you recall, if we were given a function like this, f of x equals x cubed plus 4x, or if f of x equals 3x squared minus 4x, we would have to establish the difference quotient by substituting f of x plus h and f of x into the definition of our slope of our tangent line. And so we'd have to sit down and calculate the limit as h approaches 0 of f of x plus h minus f of x divided by h. And in doing so, for these examples, they're not too bad. This one gets to be a bit challenging because we're going to substitute x plus h inside of h cubed, and we might use Pascal's triangle to expand that. But manually speaking, we could probably handle these with the fair amount of algebra. But we shouldn't always have to do that, especially if the equations start to get more complicated than polynomials. This can be quite challenging. I'm going to switch over to my completed notes for the day, and I'll just show you what the math would look like when establishing the difference quotient for these two examples. Now on this screen, I did write out Pascal's triangle for the first 4 rows, technically 3 rows plus the initial starting position. It's the coefficients 1, 3, 3, and that should say 1, not 11. 1, 3, 3, 1 that allows me to establish the coefficients when expanding something that's raised to the 3rd power. So I don't know if you can notice it here, but the 1, 3, 3, 1 act as the coefficients when I expand x plus h cubed. And there's an interesting combination for the exponents when we see that as well. Let's talk about that in class when we see each other if you'd like to learn more about that. But the bottom line is this. We started with our original function f of x, and we used this limit definition to determine a function that would give us the slope of a tangent line at some point x, because we're calculating the limit of this function as h approaches 0. And we ended up with an equation 3x squared plus 4. Now that's kind of helpful because while we know that the slope of a curved line changes frequently, this equation down here tells us, well, just plug in the x value that you're interested in, and when you substitute that in place, well, then you've got your slope. So as it turns out here, this problem was asking about the slope at x equals 1. So when we substitute x equals 1, we find the slope at that position is 7. We'll talk a little bit more about the tangent line in just a moment, but for right now, I want you to look at the original function f of x and the resulting slope of the tangent line function. I want you to start looking for patterns, and maybe you've seen some already in the examples. How did we go from this original example or original problem to this result? Do you notice any similarities between these two functions? Similarly, I want you to consider this function over here, 3x squared plus 4x, and the slope of our tangent line ended up being, or the equation for the slope of our tangent lines ended up being 6x minus 4. Do you notice a pattern here? Well, I hope that you do see the pattern, and I'll just go ahead and point it out. What we see here, whoops, too much. What we see in both of these cases are polynomials, right? So we sometimes call this the polynomial rule or the power rule for computing a difference quotient, power rule or polynomial rule. And essentially the power or the exponent that's associated with some variable will come down and multiply by its leading coefficient. So in this case, 2 times 3 is 6. We end up reducing that exponent by 1. So this 2 reduced down to 1. And then we would just repeat that for every term in the polynomial. So the implied exponent of 1 here multiplies by negative 4. We reduce that exponent to 0, and it essentially disappears. And that's where this result comes from. Similarly, we had that over here in this polynomial. 3 multiplies by the leading coefficient, which is 3. The existing exponent reduces by 1, and we repeat that for every term within the polynomial. That's the shortcut that we see for these examples. So if we switch over to today's notes, and actually let's review this definition before we go to one more example. The name that we give this process, now notice here again we're talking about the limit of the difference quotient, is what we call the derivative function. So rather than talking about this as the slope of the tangent line function, that has a special name in calculus, and the slope of a tangent line at any given point is known as the derivative. So from here forward, when we talk about slopes of tangent lines, you'll hear me use the word derivative. And also we have this new notation. Instead of f of x, we use an apostrophe here. We call this f prime of x. You may have heard that phrase before in, say, a geometry class. We reuse that naming scheme here. So we have f prime. That's the first derivative of a given function, or the steepness of tangent lines at that particular point. There are times where we would find second order and third order derivatives, and we can just add additional apostrophes to do that. So this would be the second derivative of function f, and a third derivative, and so on. It does get to be a little bit messy when we start computing past the second and third derivative, and so occasionally you'll see textbooks use this notation here as well. So this would be a fourth derivative, and we can go up to a fifth derivative, and so on. At another time, we'll talk about the meaning of each of those, but for right now, we'll focus on first derivatives. And then I also want to point out, too, that this is the notation we use when our functions are built with f of x notation. If we had an equation such as y equals, say, 3x squared plus 2x minus 1, well, we can't really use f prime here because the function was built on the letter y. And instead, we use a slightly different notation that looks like this. Oops, wrote that backwards. dy dx in this case. And this is what's called Leibniz notation. Again, we'll spend some more time talking about that in class. And with Leibniz notation, one way that you can read this is simply saying the derivative of y with respect to x. So we're finding the derivative of the function that's named y based on the variable x that exists in the problem. So dy dx or f prime. We'll practice with both of those notations as we go. So to finish out this particular video, let's just talk about this particular example here. We have a function f of x equals negative 16x squared plus 96x, and this was the function that described the motion of an object that's being thrown in the air upward at 96, I think it was feet per second. We know that the object goes up and it comes back down, and at some point it sort of levels off while it's in the air. If that function, let's see, I do have a picture of it here. If that function has a y-axis representing feet and an x-axis representing time in seconds, then the slope at any given point represents the velocity of the object in feet per second. And so this graph here kind of shows us that, and it's also saying that our derivative is negative 32x plus 96. And hopefully that makes sense. If we took the power 2 and multiplied it by negative 16, we get our negative 32. Reduce that exponent by 1. And then this power of 1 got multiplied by 96, and we reduce that power by 1 to get x to the 0. And then that term essentially disappears. So this is our derivative function, very quick to compute now that we don't have to go through the entire difference quotient. And if we were to substitute values into that, and the screen is a little bit blurry here, but that's essentially what we've done. We're taking the number 0, and we're substituting it into the prime notation function, so negative 32 times 0 plus 96. Well, clearly that equals 96. That math's not too hard to do. And if you think back to the original problem when I introduced this a couple weeks ago, we were told that the object was thrown in the air initially at 96 feet per second. And as gravity acts on it, the speed that the object is moving is slowing down because gravity is trying to pull it back down. We said that by the time the object reached by the time 3 seconds has passed, the object has reached the apex of its path, and that's further supported by this claim. If we substituted the number 3 into this equation, we now have negative 32 times 3 plus 96. Now, negative 32 times 3 is negative 96, so when added with 96, we get 0. And again, this should make sense because when we consider our units, and I'll make them stand out a little bit here, feet per second, this computation represented our initial velocity. This one represents our velocity at 3 seconds, and we can do that for any time along the path here. And so that very quickly allows us to compute what we call an instantaneous rate of change, in this case instantaneous velocity, and this just opens up a whole new world to us in terms of mathematics and utilizing functions that represent positions of objects with respect to time. So when we see each other in class next time, we'll talk a little bit more about some other simple rules for computing derivatives. They're not quite always this straightforward as the power rule, but we have several rules that have been established, and then we'll talk about how to establish them ourselves. We may even talk about computing the derivative using the difference quotient one more time for interesting examples, just to illustrate the point that all of the rules that we establish come from formal proofs that support the claim. But for right now, I know this video is getting a little bit more lengthy. I hope that I've done a fair enough job explaining how the slopes of tangent lines can be quickly computed, and in class we'll talk about other rules as well as ways to find the actual equation of a tangent line to a graph at a specific point. Thanks for watching.